Hello, everybody. Today we will be discussing about electromagnetism, Faraday's law, and Lenz's law in detail. This class will be for 30. Let me create 30 minutes. 30 minutes. Okay. Um, this class will be for 30 minutes, and we will be right. And we will be discussing about all of this in next lectures. All right, now let's start. We will start in detail of everything. All right, let me just go through it. So what do we know from our prior knowledge? We know that if there is a conductor, let's specifically call it a current carrying conductor. If there is a conductor, a current carrying conductor, a current is flowing in that conductor, then what we know is that it will create a magnetic field around it. It will create a magnetic field around it, and that direction is given by the right hand rule, where thumb gives the direction of current and the fingers curled gives the direction of a magnetic field. So we know this basic information. All right, now, knowing this, there is a current carrying conductor, a current is flowing through it, and it produces a magnetic field. All right. Now, many years later, Michael Faraday came and he saw this. What he saw was a steady current. What he saw was a steady current was producing a magnetic field. A steady current was producing a magnetic field. All right. See, it is not only the steady current that produces a magnetic field. All right, even if the current is changing, let's say varying current or alternating current, whatever you might say. Okay, alternating current also produces magnetic field. But here, what we are trying to see is we are basically concerned about steady current producing a magnetic field. So steady current is producing a magnetic field, then the vice versa, the reverse also must be true, isn't it? Because that's the Newton's third law of motion. And a third law on anything not of motion. Okay, that's Newton's third law, not on motion. Because nature, Newton's third law always exists. All right. So, because that's Newton's third law, the vice versa also must be true, isn't it? Now, what happens is Faraday, Michael Faraday, does one experiment. The experiment goes like this: he creates a circuit. He creates a circuit, and here he creates a solenoid. Why solenoid? Because the magnetic field, we are creating a magnet out of it. All right, because if current flows, then we will go and then we will have a magnet. Now let me just have this. Let me just have this. Okay, now we have a switch, we have a battery, and we have a solenoid. All right, let us assume I'm just choosing the direction of current arbitrarily. Please do not, you know, tangle into it. So for example, let's say the field is happening this way. All right, field is happening this way. The field is happening this way in the same manner in the next direction. All right, the field is happening this way. Okay, now what Faraday did was, if 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 the current is producing magnetic field, then magnetic field also must produce current, isn't it? Magnetic field brought to near a current carrying conductor which has no current. We brought a current carrying conductor which has no current, and if this interacts with a magnetic field, then there must be current induced in it, isn't it? That's the opposite we are trying to find out. So let me just what Michael Faraday did was he attached a different loop in it. He attached a current carrying conductor, okay, looped current carrying conductor in it. Let's say this is the loop. Let's say this is loop 1 and this is loop 2. Okay. So whenever there is a magnetic field, whenever the circuit is open, whenever the circuit is closed, I'm sorry, whenever the circuit is closed, there is a magnetic field on loop 2. There is a magnetic field is produced by loop 2. But whenever this happens, Michael Faraday couldn't find any current here in loop 1. See, Michael Faraday couldn't find any current in the loop 1, just because the circuit loop 2 circuit is closed, the circuit is complete. Because of that, solenoid is producing a constant magnetic field, and on that constant magnetic field there is a second loop number 1, where it is a current carrying conductor, but in that current carrying conductor there is no current. That means no current is induced when the current carrying conductor is in interaction with the magnetic field. Now, Faraday was very pissed off by this, because the steady magnetic field we are talking about, is not being able to generate a steady current. Then what is the vice versa is not true, isn't it? The nature's law is failing. But one day what happened was, Michael Faraday was just investigating on it, and what he found was, he found a very interesting thing. What he found was, when he closed the switch at that instant, and when he opened the switch at that instant, 2 instant, please, the change of time, 2 instant. When he opened, let me call it instant number t1, time 1, okay, and this is time 2, let me call it time 2. So on these 2 instant, on time 1 and time 2, when the circuit is closed and when the circuit is open only for a small period of time, when the circuit changes, then what he found was there was a current induced in it. Again, please, I'm choosing arbitrary direction of the current, so please ignore it. There is current induced in it. All right, there is current induced in it. Now he realized it is not the steady magnetic field, it is the change in magnetic field that is producing current. It is the change in magnetic field. When the switch is closed, magnetic field changes. When the switch is open, magnetic field changes. All right, so only at that time magnetic field is changing. So it is not the steady magnetic field that is producing steady current, it is the varying magnetic field or change in magnetic field dB by dt. It is the change in magnetic field that is producing current, that is producing induced current, that is producing induced EMF. Let me just write it, induced EMF. So we have come to this, we know this now. It is the change in magnetic field that produces EMF. Okay, so this is what Faraday found by his experiment. Now what did Faraday do was, Faraday did some different experiment. Let me just explain the next experiment to you guys. Faraday did a lot of experiments. Okay, so what next Faraday did was, Faraday did something like So here is the loop 1, okay, and here is loop 2. So loop 1 is connected to a circuit. Loop 1 is connected to a circuit, okay, and loop 2 is not connected to a circuit. Loop 2 has an ammeter because current is induced, because current is induced by the change in magnetic flux from loop 1, okay, by the change in magnetic flux from loop 1. This is, let me just write it this as a case 1, and we have a case 2, okay, where we have, here we have two loops, here we have two loops, okay. Please see this, this is very important, this is very non-intuitive thing, okay. We have two loops. Here we will be only having one loop. For example, let me take this 3D, a loop of a wire, and let me just make a bar magnet, okay. Bar magnet, let me say this as a north and this as a south. So the field lines will go in such a way, okay. So field lines will go in such a way. Now what we have is the field line is going in such a way, okay. So if I bring that bar magnet near to the loop, what I am doing is I am making the field increasing, okay, increasing towards the loop, increasing, okay. Please see this, it is increasing towards the loop. So we will again learn the different concept right here, right away. So the magnetic field line is increasing. Now the magnetic field is pointing downward, okay, increasing. Now what happens is the current will be induced, but the induced current, the direction of induced current will be in such a way that it will oppose the change that is creating it. What is creating the induced current? The magnetic field downward. Increasing is creating a magnetic field, isn't it? Now it will oppose the field downward. It will create field upward. Okay, it will create a field upward. So while creating a field upward, the current will go in anti-clockwise direction. So this is the direction of a current, and my dear students, that is what we know as Lenz law. It's a very simple law, okay, but very profound and one of the very important law. Conceptually, it is not a quantitative law; it is a qualitative law. We cannot know how much current, the power and the stuffs. We will be only be knowing the direction of a current. So this is Lenz law, and Lenz law is very human law because human have a tendency to resist a change, and it will resist a change. So it is most human law, and this is Lenz law. And here my what I'm trying to make you understand is, you understood Lenz law, all right. Now what I'm trying making you to understand is, here we have, in on case 1 we have two loops, loop 1 and loop 2. On case 2 we have only one loop, all right. So the EMF induced in loop 2, EMF, please see this, EMF in 2 is directly proportional to the dB change in flux, change in magnetic field in loop 1, in loop 1, okay. Please see this, this is very important, in loop 1. And again, EMF, EMF in EMF in loop 2 is directly proportional to the area in loop 1. But here we have two loops, okay. Here we have only one loop, so area is accountable. In second case, area is accountable. If there is more area, okay, then more current, okay. The area and current, if there is more area, there is more current. This is second case. But here, even if we increase the area of a 2, or decrease the area of a 2, it will have no effect because EMF is totally dependent on area 1. Why is that so? It is very non-intuitive. Please see this. It is very non-intuitive because the change in magnetic flux, the change that is happening is confined in area 1. Okay, is confined in loop 1, is confined with loop 1. So for example, let's take a balloon, all right, and let's say there is a high density something is there, and it is generating flux. So if even if I make the balloon size small or bigger, the total amount of flux that is coming out, the total amount of flux that is changing is essentially from that um, high density something that is confined inside it. Let me just draw it. For example, let's say I have a balloon, okay, and I have here high density something that is creating a flux, and the flux is coming outside. Okay, flux is coming outside in a way. Okay, it is diverging. Now the amount of divergence does not depends upon the size of whatever we are considering. For example, here, even if I decrease the size to this, the amount of divergence is same because the same amount of flux is coming out. Are you getting the point? The same amount of flux is coming out. It is not the different amount of flux. Even if I make the size this big, the same amount of flux is coming. Imagine there is a water, all right, no matter if I make this big or this small, the amount of water that is flowing out is same. No different amount of water, isn't it? It is same amount of water. That is why we are saying the change is confined in this area. The change in confined in this area one, in this area. Okay, the change is confined in this area. That is why EMF is dependent on the area of this one, not on the area of this one. And dB by dt is also defined on this one, because change is essentially happening from here. It is not happening from outer imaginary circles that we have made. The change is essentially happening from the confined part, the diverged part. Okay, change is essentially happening from the diverged part. So that is why loop 1 is very essential. It is very very essential, all right. So we have two cases where two loops. We have two loops condition and we have one loop condition. All right. So on one loop condition, no matter what, this loop is very important because that is only loop we will be able that loop is there. It will define the change in magnetic flux through that loop, and it will area of that loop also will be very very important because that's the only loop. Okay, so this is the very non-intuitive concept you will find. Now next very important thing that you will need to understand is, for example, on loop on for example, let me just make it like this. For example, I have this loop and I have this loop is three times. Okay, this loop is three times. This is primary loop, this is secondary loop. What Faraday found was the area is independent. Okay, area does not cares. No matter, you might have big area, you might have smaller area, there is no change in any EMF produced. But because here we have it, we have the proof, EMF is not dependent on area 2. It is not dependent on area 2. EMF is not dependent. But what he found interestingly is that if we make a loop, if we increase the turn, then the EMF is increased proportionally. If we make the turn twice, then EMF is increased by two times. If we make the loop thrice, then EMF is increased by three times. This is again very one of the different results. Okay, so EMF is dependent on the number of EMF is directly proportional to the loops, number of loops, number of loops. Okay, number of loops. EMF is directly dependent on number of loops. Please see this. So we have completed this concept. You have understood what is Lenz's law. You have understood how EMF is affected and how EMF is induced. Okay, on what basis EMF is induced. Now we will be entering on next important topic where we will be discussing about same thing but about flux. We will be discussing about same thing. What's the time remaining? 9 minutes. Okay. We will be starting. Let me do one thing. I will start this on the next lecture. I will just leave it on this. If you have any questions till now, because from the next video I will start magnetic flux that is relating to electromagnetic induction. Till now, if you have any confusions, please let me know by comments. And if you have any questions, you can ask me by comments, and I will definitely answer the questions. If you have any confusions, if you have any feedback, please leave in the comments. Thank you for this. So I'll be leaving now today. Take care. We will be on the next class. I'll see you on the next class.